Hello, TIC/BC Part 1. It is Monday, and I really enjoyed the class we just had. You all are all doing really exceptional work in a really demanding and challenging math class, and so I just wanted to give you all a big collective pat on the back. So now, after my long-winded lecture about derivations, and never, ever accepting something as true unless you see a derivation, I am, for the purposes of this screencast, and just not bogging you down in algebra on a screencast, I am going to tell you or give you these four brand new identities, and I'm going to say these words, and I think you're going to say, and I know Daniel, you're going to say, Miss Yam, how dare you take back what you said in class? And you know what? I think I'm going to do it, and I'll just take Daniel's ire when I see him next, okay? Let me give you these four identities here in this screencast, and then we will do a derivation together in class when I see you on Wednesday. So these are going to be four new statements, identities for the sine or cosine of a sum or difference of angles, okay? The first thing I want to make sure you understand is that this would be very careless to say that one could distribute sine to the two angles theta and alpha, okay? Sine of theta plus alpha is not the distributive property, okay? So let's just make sure we understand that. This is not the same thing as saying, for example, 7 times x plus 3. Number one, there is no multiplication here, okay? This is sine of. Okay, so this is not this expression here, the sine of, say, 10 degrees plus 14 degrees, okay, while that would equal the sine of 24 degrees, right, that does not equal sine of 10 degrees plus sine of 14 degrees. So your question is, what is the sine of a sum of angles? And let me tell you. So the sine of theta plus alpha is going to be the sine of theta, okay, times the cos of alpha, okay, plus the sine of alpha times the cosine of theta. All right, the sine of theta minus alpha is the sine of theta times the cosine of alpha minus the sine of alpha times the cosine of theta. Now, hopefully you are all having the appropriate reaction, which is, what? Where did this come from? Why is that true? How is that true? And I guess I'm stuck with one of two things. I could do the derivation right now. It's a bit long-winded, and it's not hard. It's just long, and it's a bit algebraically heavy. But I just wanted to get this out to you so you can start doing the homework. You know what I'll do? I'll do a separate screencast where I derive these identities. Oh, I also have to derive the law of cosines for you, I think, don't I? Or did we do that? Can someone remind me? I don't remember. Anyway, okay, so why do we use these identities? Well, there's two places, and I'll come back and do these two in a moment. There's two ways, there's two reasons why or how we could use these. One is, I could say, now I'm going to work in degrees. We could actually find the sine of 75 degrees, okay, without using a calculator. And the reason why I could find 75 degrees without using a calculator is because I can express 75 as a sum of two angles that I do know, okay? And this then allows me to say, oh, okay, I can then use this, which then allows me to do this. And at the end of the day, I have the sine of 75 degrees, radical 3 plus 1 all over 2 root 2, okay? The other place that I could look at using identities like this is if I was asked to prove an identity. Oh my goodness, remember those from back in the day? I'm going to show you, I'll give you an example of one of those after I show you or tell you, because I'm just telling you, right? I'm not actually showing you. And I think there's a difference between telling and showing. And you're hopefully saying, Miss Yam, now that you've told us, you better show us. And you know that I will. Okay, let me give you the cosine sum. And I'll give you a little shortcut for memorizing these too. Okay, I promise. I hereby promise I will absolutely derive these for you. One way that is kind of cute to remember these is to remember that the cosine sum and difference, cosine is clustered, right? Cos is with cos, sine is with sine, cos is with cos, sine is with sine. Cosine is clustered with the opposite sign. So the cos of sum has a subtraction, yeah? The cos of a difference has a sum. Sine, look at this, sine of a sum, it's sine cos plus sine cos. So I like to say sine is all scrambled up, like it goes sine with a cos and then sine with a cos. Sine is all scrambled, but it has the same sign. So the little sing-song I have is sine is scrambled with the same sign and cosine is clustered opposite sign. But that's neither here nor there, okay? All right, these right here, by the way, and if in case you're wondering, is there a tangent of theta plus alpha? There absolutely is, and we will derive that together in class. So in class, not only will I derive these, but then we will derive the tangent sum and tangent difference. These are called the sum and difference identities, and hopefully the name of these identities makes sense to you. These are called the sum and difference identities, okay, because they give you a way to find the sine or cosine of a sum or difference of angles. Okay, I told you that one application of these could be a problem like this, evaluate sine of 75 degrees without a calculator. But we could also be asked to prove identities. Do you remember identities? Okay, prove the following identity. Oh no. Why are you asking me that question, computer? I don't want to set up this pen. Okay, I'm just pulling this from the packet I gave you. It's the page 139, and I'm looking at number 48, okay? That little packet of handouts that I gave you that I said we didn't have homework on until tomorrow. And once again, I've surprised you again, so we actually will have homework on this. Okay, cosine, this looks like this. Identity is this one, the cos of 2x. Oh, I think my 2 is on steroids. Oh goodness, what happened here? Okay. Prove the following. 48 says the cosine of 2x, okay, times the cosine of x, plus sine of 2x times sine of x equals -1, okay? Prove the following. Prove this identity. Now, a couple of things. You'll notice that when you look at how this is written, okay, cos 2x times cos x, the implication, the understanding is we're looking at the cosine of 2x times the cosine of x. It is understood that, for example, that 2x cos x, that the argument of this cos is not 2x cos x, okay? It is understood that this expression is saying cosine of 2x times cosine of x. Similarly, the sine of 2x times the sine of x. All right, let's prove it together. We usually say when we have an identity where one side is far simpler than the other one, we like to say, let's work with the more messy side, okay? Now, I guess a couple of things. Maybe you're someone who already sees, oh my goodness, that this is a cosine is clustered going on. There's a cosine clustered going on, right? It goes cos, cos, sine, sine. And maybe you're saying, I kind of see that this could be like cosine of 2x, right, times the cosine of x plus the sine of 2x times the sine of x, right? And you look at this identity over here, boys and girls, look at this. Cosine of box times cosine of x plus sine of box times sine of x. Well, guess what? This just equals the cosine of box minus x, right? And this is just cosine of 2x minus x, correct? and 2x minus 1x equals the cosine of 1x. And the cosine of 1x equals negative 1. And I am, oh, for heaven's sakes, Yam. Number 48, look at the directions for number 48. This is not a prove the identity. This one is saying solve the equation to find the value of x or theta. Oh, well, Miss Yam. Oh, okay. Then it says solve. Oh, for good grief. Solve. Sorry. Well, look. Now we have yet another application. We can solve equations. Okay, so now we have to solve. Okay, so we're solving. Well, so what do we do? When we have to solve this equation, the first thing I'm looking at is saying, if this is a trigonometric equation, I want to do all that I can to simplify, right, and get down to an equation with, with one trig function and as simple as an argument as possible. So I just did that. Now it says, part A, it says solve for the general solution for x or theta in terms of multiples of 2 pi or multiples of 360 degrees. Okay, that means we're finding every possible solution. And then part B says solve for the particular values of x in the domain of x between 0 and 2 pi, or x between 0 degrees and 360 degrees. Fantastic. So we're going to solve this under both conditions. Part A is asking us to solve for all possible solutions. Well, let's see. Cos of 1x equals negative 1 is the same thing as saying the inverse cos of negative 1 will equal x, right? Now, I know on my calculator, if I input in inverse cos of negative 1, I will only get one solution, right? And I know that that x here is going to equal pi. But I want to solve for, part A says find the general solution. General solution means all possible solutions. So x equals pi, or 180 degrees. But x could be pi or any multiple revolution of 2 pi plus pi, or 360 plus 180 degrees, right? Any angle that will land on the same terminal side as pi. And the way we write that is we say x could be equal pi plus 2 pi n, where n is some integer. N is understood to be some integer. We're saying that x could be 180 degrees or any multiple revolution added to 180 degrees. Okay, but now part B says only solve for values of x between 0 and 2 pi. Okay, so then for part B, we would look at this. So we're saying only the values of x between 0 and 2 pi that has a cosine of negative 1. This would just be x equals pi. Oh, look at us being forced to revisit old stuff, and aren't we so glad we then spiral through our material this way, right? Always going back and forth, forcing us to be comprehensive. Okay, fantastic. So the homework tonight is going to be the following. On that packet, it's page 138, 139, okay? And please read the directions before you launch into a problem. And yes, I realize some of you are saying, Ms. Yam, are you saying that we should do what you say and not what you do? And I guess the answer to that question is yes. And I tell my children that as well when they watch me drive. I say, you should never run through this red light, even though I am running through this red light. But that's for another story for another time. Okay, numbers. Here we go. 23. Okay. Let's see. Ooh, I like 27 and I like 31 because 31 asks you about the secant of 15 degrees. And can you kind of make the leap between secant and cosine, okay? And then by similar extension, let's do 37 as well. Okay, and then I think I want you to do 45, okay? 45, 47, 51, 54, and 56, 51, 54, and 56. Okay, tomorrow being Tuesday is our drop day, and I am going to put up something else to do, which is, oops, hang on a second. I know that I'll put up some more homework for tomorrow, but I wanted to get this out to you at least now. Okay, goodbye, class.